Good evening in India and good morning in US.
Good morning.
Morning. Now I am inviting Professor Nathan Dunfield for his lecture on counting essential surfaces in three manifolds. On behalf of Professor B.L. Sharma Higher Mathematics Trust, I am really grateful to Professor Nathan Dunfield for accepting our invitation. Professor Dunfield.
Thank you. It's a pleasure to be here. So I want to say that the slides for the talk are posted at this URL if you want to follow along. And this is the paper that this work is based on. Feel free to interrupt me with questions, either in the chat or raising your hand or just speaking. I'm happy to answer any questions you might have. So let's just sort of set the stage. So what are we going to be talking about? So we're going to be talking about three manifolds, let's say compact orientable three manifolds. So think maybe the three sphere or the three torus, or maybe a lens space, standard example from algebraic topology, or maybe you could take a surface of genus G across a circle, something like that. I'm going to be working with irreducible three manifolds, which means that I don't want to look at connected sums. I want to break them down into these irreducible pieces. So in particular, this means that every embedded two-sphere bounds a ball. And we're going to be interested in surfaces in these manifolds. And I'm going to make an assumption, kind of a technical assumption, although an important one, that any embedded surface in my three manifold is orientable, any closed embedded surface. So for example, if you impose this condition on the homology, that's arranged. But this is sort of a technical thing which you can ignore. As in many areas of topology and geometry, one place to start studying an object is to look at its hypersurface, that's codimension one object. So in this case, this is simply the surfaces. And well, what kind of surfaces do we want to look at? Well, all right, I mean, we're in a three manifold, right? So every point has a neighborhood that looks like a ball. So in particular, let's say a little genus 2 surface sitting in a neighborhood of that point. That surface tells us nothing about the global topology of this particular manifold. And so we want to look at surfaces that are basically the opposite of the surface I just drew, surfaces that are topologically essential. So the notion here is that of incompressibility. So let's say that a closed connected embedded surface, we'll call it incompressible when it's not the two sphere. Right, so this irreducibility assumption means there's no interesting two spheres in my manifold. When it's not the two sphere and the map on fundamental group is injective. So the map reduced by inclusion from the fundamental group of F to the fundamental group of M, that's injective. So that in particular excludes a picture like this. For example, this loop here on my surface, that's a non-trivial element of pi 1 of F, but you can see we can homotope it to a point in the ambient manifold. So this is an example of something that's not. Sorry, was there a question? So what is an example of a incompressible surface? So like maybe we look at this example here. If we take surface cross point, it's a nice surface sitting inside surface cross circle. Its fundamental group is factor of the fundamental group of the whole manifold. So that's a good example of an incompressible surface. So I'm actually going to allow my three manifolds to have boundary. And when I do, I don't want to think of the boundary of that manifold as a incompressible. I mean, it is an incompressible surface, but maybe not one I want to talk about. So if I have boundary and the surface is not parallel into the boundary, we'll call that essential. So the goal for today is to count closed essential surfaces in M up to isotopy. So I'm working here in the smooth setting. If I have two surfaces, I might be able to homotope one to the other through embeddings, an isotopy. I'm going to consider such surfaces the same. I'd like to try to count these things. So let's just see some examples. Okay, so like, for example, first example might be the 3 torus, right? So the 3 torus has a lot of essential surfaces, like for example, S1 cross S1 cross point. Also S1 cross point cross S1. But in fact, you know, it's really more symmetric than that. You can think of the 3 torus, right, as the quotient of Euclidean space by lattice of translations. And from that perspective, you see that every primitive second homology class is actually represented by a torus. So there's a lot of essential tori in this manifold. On the other hand, any essential surface in the 3 torus is going to be a torus, a 2-dimensional torus, because you know the fundamental group, right? Whenever we have an incompressible surface, the fundamental group of the surface is a subgroup of the fundamental group of the manifold. And consequently, since in this case of the 3 torus, the fundamental group is Z cubed, the only surface which can sit inside there is the 2 torus, because if you have genus 2 or something, the group becomes non-abelian. So that's an example where we have lots of things to count. Another example is where the count is simply 0, would be any 3 manifold where the fundamental group is finite. So for example, the 3 sphere, one of these lens spaces, fundamental group is a finite cyclic group. Those can't contain an essential surface because, again, you know, we're talking about an orientable surface of genus at least 1. That is infinite fundamental group. So it's not going to sit, its fundamental group can't sit inside the fundamental group of a manifold like this. Okay, so we have some answers where it's infinite, some where it's 0. Another class where it's 0 that'll be important for us, kind of family of examples, is so one way to make lots of 3 manifolds with boundary is to take a knot. So that's a smooth embedding of the circle into the 3 sphere. So I'll draw here the figure 8 knot. And then we could look at the exterior. So that is, we take the 3 sphere and we remove a little neighborhood of the knot. So I don't know. So we kind of thicken this thing up. And the little neighborhood will be this open solid torus. And then what's left? Everything outside. Plus the point at infinity. That's a compact manifold whose boundary is a torus. And so another example where there aren't any surfaces, closed essential surfaces, is this setting of Hatcher and Thurston, that if we take what's called a 2-bridge knot, which is just some special class of knots, it's not particularly important what it is, figure 8 knot I just drew as an example, then such knots have no closed essential surfaces in their exteriors. Maybe it's a good time to pause. Other questions? All right. So we've seen counts of 0 and infinity. However, there are other cases where the counts are always, the counts are never infinite. So we'll say a 3 manifold is atoroidal when it contains no essential tori. And the fundamental example of such manifolds would be, for example, the ones that are hyperbolic, the ones that admit metrics of constant negative sectional curvature. And by the work of Thurston and Perlman, this is a very important class of 3 manifolds, one of the fundamental sort of generic building block of compact three manifold. So this is the setting that we'll be looking at. And in this case, it goes back to the work of, I think, Haken or Waldhausen in the 70s, that for atoroidal manifolds, these counts are always finite. This phenomena that we had with the three torus, with their infinitely many tori, if you don't have any tori at all, then you can't have infinitely many surfaces of a fixed genus. So it makes sense then to talk about this number, AM of G. So this is just a number of genus G essential surfaces up to isotopy. So let's see just an example of these counts. So I'll again use one of these knot exteriors. So this is, I drew here, this is the Conway knot. And the exterior of the Conway knot is a hyperbolic manifold, it turns out. And here is a table of the counts of surfaces of various genus. So in genus 1, there aren't any. That's just saying that this is an atoroidal manifold. There are 6 essential surfaces of genus 2, 9 of genus 3, and then, well, the numbers just keep increasing. And, you know, all right, there's 444,038 essential surfaces of genus 100. Right. Well, that's quite a list of numbers. And of course, this begs the question, you know, what's the pattern? I guess it probably also begs the question, how did I compute these numbers? To answer my first question, I simply have no idea. So the sequence of numbers isn't, you know, you can go to the online Encyclopedia of Integer Sequences, type in these numbers, it says no idea. So far, we don't have a, you know, we don't know what the pattern is that these represent. So, well, okay, now you might think this is going to be a brief talk, but of course, I would still have to tell you how I computed these numbers in the first place. But in fact, well, I don't know what this sequence of numbers is. There's actually a related sequence which turns out to have a lot of structure. And that sort of is our main result. So let's count a slightly, well, let's count a larger collection of surfaces, right? So for the thing I was just talking about, you know, we're talking about counting surfaces of a fixed genus, so that particular connected surfaces. But instead, we could allow ourselves to count surfaces that might have multiple components. So this function Bm of minus n counts essential surfaces whose Euler characteristic is minus n, again, modulo isotopy. So, you know, in particular, or I guess AM of 2, number of surfaces of genus 2, that's actually the same as Bm of minus 2, since, of course, Euler characteristic 2 minus 2g for our surface. On the other hand, if I look at, say, Bm of minus 4, so one way we could have a surface of Euler characteristic minus 4 is, of course, surface of genus 3. So this is actually going to be AM of 3 plus another way we could have a surface of Euler characteristic minus 4 is 2 surfaces of Euler characteristic minus 2, that is, say, 2 surfaces of genus 2. So this is going to be equal to A3 plus the number of essential surfaces that look like the disjoint union of 2 surfaces of genus 2. So, okay, and of course this contribution here, this actually includes the A2 thing. I mean, if you take a single essential genus 2 surface, you can take 2 parallel copies of it. That will be something we're counting in Bm of minus 4. But you might also have cases where you have 2 surfaces of genus 2 that are actually not isotopic. And we'll count those as well. So then for the example where I had this long list of these apparently random numbers, if we instead count surfaces independent of whether they're connected, then actually it turns out there is a closed formula for the count. So this is the Conway, this is the exterior of the Conway knot from the previous slide. It turns out that this is the exact function for the number of surfaces of oil characteristic minus 2m. It looks like it's basically a polynomial, a cubic polynomial with rational coefficients, except for this last term, which oscillates back and forth between 1 and 3/4, depending on the parity of n. So this kind of function, this is what's called a quasi-polynomial. It is something that shows up frequently in algebraic combinatorics. There's a rich theory of these functions. I'll explain one of the origins in a bit. But the exact definition isn't important. It's just basically a polynomial where maybe some of the coefficients oscillate mod some period. So this closed formula is not actually specific to, I mean, the fact there is a formula like this turns out not to be specific to the Conway exterior. So we prove a general theorem, which is that for any toroidal 3-manifold, the counts, these BM counts, they always satisfy this kind of structure. So the concise way of saying that is we can assemble these numbers into a formal generating series for variable x, and then one way of saying it's a quasi-polynomial is to say that this generating series is a rational function, polynomials p and q with rational coefficients, where q is a product of cyclotomic polynomials. But I mean, I should have probably just written this as saying that for any toroidal 3-manifold, this count is a quasi-polynomial. And in fact, we do more than just prove this sort of an abstract statement. We give an algorithm which, given a manifold, can compute the p and the q, can find the quasi-polynomial, and it also like list the surfaces of any particular Euler characteristic. Let me pause there. Are there questions?
Yeah. So is it like our BM of minus 2n is always non-zero? Like, do you have an upper bound?
No. Of course, they might simply be 0. And in fact, so for example, for the exterior of a 2-bridge knot, they're simply 0 for all n.
So there are 3 manifolds where you can find an essential surface of any genus. Is it like any arbitrary genus?
Well, yes. I mean, for example, I believe this one has yes. There are certainly 3 manifolds for which you have essential surfaces of every genus. There are also ones where there simply are no surfaces of any genus, and all sorts of behaviors in between.
So this polynomial on the left-hand side in the theorem can be a finite polynomial, right? And that cases are. Yeah,
I mean, the counts are always finite.
Yes, but yeah, but I'm saying like finite degree polynomial. That is what it could
be. Oh yeah, the finite
degree.
Absolutely. Okay.
Thank you.
And of course, that brings up the question, like, what does the degree of this polynomial mean? Like, what does it mean that this is an n cubed as opposed to n squared? What do these coefficients mean? These are all invariants of the manifold, because these counts were described purely in terms of the smooth topology counting surfaces. And that's something I'll talk about in a bit. Are there further questions? Okay, so this is the theorem I want to talk about. The next thing I want to do is I want to kind of explain where this comes from, and in fact, sort of this will involve explaining a little bit about the algorithm, how you work with surfaces like this, and and I'll kind of hint at where the theorem comes from, and then I'll talk a little bit about some open questions. There's still a lot that we don't know here. Okay, so yeah, so we'll think. Okay, so we have our three manifold here, M, and let's look at a triangulation. Let's call it T. So by that I just mean a simplicial complex, whose underlying space is M, so just some finite number of simplices, three simplices glued together. And we're interested in surfaces, right? And so, okay, we can look at our surface. How does it meet these tetrahedra? And well, of course, it could be quite complicated. Maybe our surface meets it. Of course, it could be a bunch of components. Maybe there's like one component meets its little disk. Here's an annulus. Maybe one component of our surface, just this free-floating torus. So we're going to focus on what are called normal surfaces. So these are ones that meet the tetrahedra of our triangulation in pictures that look basically like what I've drawn. So in particular, the surface meets each tetrahedron in what looks like a bunch of planes slicing through the tetrahedron. So in particular, in a normal surface, they're going to be, one way a plane can slice through a tetrahedron is to chop off a vertex. So there'll be four kinds of triangles that might appear as part of a normal surface. The other way a plane can cut through is to separate two opposite edges. So we have pieces like this. These are called quadrilaterals. There's actually three kinds. Let's see. So there's one already drawn here. Here's another quadrilateral. And let's see, where's the last one? Oh, the last one will be here. So you can sort of see from the picture I just drew, you never have more than one kind of quadrilateral at once if we're talking about an embedded surface. So there's 7 different ways that, so a normal surface is built up of these standard disks, triangles, and quads, and of which there are 7 kinds. And so in particular, this means we don't have pieces like this or this sort of free-floating torus. And it also means that we can record the normal surface just by a bunch of numbers, right? So, for example, right, if I wanted to describe the picture here, I could say, well, there's 2 triangles in this corner, 1 triangle in this corner, 1 triangle in this corner, 2 triangles in this corner, and there's 1 quadrilateral in the middle, namely this kind of quadrilateral. And there's no quadrilaterals of the other 2 kinds. So in other words, this picture we describe with 7 numbers. And in fact, if I have a normal surface, which is one that meets every tetrahedron in pictures like this, then I can record that surface by just a list of 7 T's, of T is the number of tetrahedra, as a list of 70 non-negative integers. And in fact, those numbers come from the surface, but in fact, it's enough to recover the surface. And maybe kind of to explain that and also to explain some of the structure, right? So if I have, maybe let's say I have 2 simplices tetrahedra in my 3 manifold. And let's say that these 2 faces here, these are actually glued together. They're actually adjacent, but let me not draw them that way. And so maybe here, is my part of my normal surface. Maybe let's say there's 3 disks, so I got 2 triangles and one of these. And then over here, maybe I have this picture. I have 1 and 1, but the picture I just drew actually isn't a valid, doesn't actually come from a real normal surface, because when I try to glue these together, right, I have 3 arcs running across along this face, and that's supposed to be glued over here, but there are only 2 arcs over there. We can't make everything line up. So if this really came from a normal surface, I'd have to I could add some additional stuff. So maybe I'll add a second quadrilateral there. So now these things do match up. And it's fairly unambiguous how I glue these together. I don't really have a choice if I'm supposed to be making these into an embedded surface. So we can actually think of the condition that these things match up along this common face as some kind of equation, because, so maybe we'll call this the number of these things. Let's maybe call that x1. Maybe the number thing here is x2. I don't know, x3, x4. So I change this to 2. The fact that I was able to match up these things in this corner when I glued up, that's actually the statement that x1 plus x2 is equal to x3 plus x4. So we can describe a normal surface as it's some lattice point in R to the 7t that records all these numbers, and which satisfy a bunch of equations that look like this. These are just homogeneous linear equations. And so, I mean, geometrically, what does that mean, right? We're looking at solutions to a system of homogeneous linear equations, but of course, we're interested in things, it doesn't make sense to talk about negative triangles, right? So we're interested in only ones where the coordinates are non-negative. So that's like you take solutions to a homogeneous linear system. So that's just some subspace of R to the 7t, and then you're intersecting it with a positive orthant in R to the 7t. And that's going to give you some kind of polyhedral cone. So that's sort of this picture I have here. So you have this blue cone, which is the solutions to the linear equations with the condition that the coordinates are positive. And then the lattice points in here, each one of these corresponds to one of our surfaces. And what's absolutely key for us is that kind of foundational technique in 3 manifolds, that any essential surface can be isotoped to be normal. Like to go back to this picture, right? We know the picture I drew here, this little torus here is not part of an essential surface, right? So you actually, by an essential surface, I wouldn't even have any pieces like this to start with. And if we had some kind of thing like this, we have to do some move to simplify the picture, which you could do if it's essential. Anyway, there's a theorem which says that if we're interested in essential surfaces, we can focus on just these normal ones. The bad news is that normal surfaces, that the resulting normal surface might not be unique. And since we're trying to count things, then we're going to have to worry about counting normal surfaces that are actually isotopic, even though they're not the same. So this is also a good point to pause for questions.
So here I have a question. So here is uniqueness means up to isotopy, or just here the resulting normal surface is far from unique?
Yeah, it just means that, like, so the normal surfaces are, for example, recorded by these numbers.
Okay.
Right. And you could have different numbers, different vectors that actually give isotopic surfaces.
Oh.
There might be some, when you move the surface through the manifold, it might become unnormal for part of it, and then the numbers can change. And so you might have different points here. Maybe, like maybe really these are isotopic surfaces. Something like that could happen. And we have to worry about that because we're trying to count them.
Thank you.
Welcome. Other questions?
Right. So about the good result we have, so does that depend on the triangulation? For
No,
instance,
no,
like,
this
do
is for
we-
any triangulation. For any
Okay.
triangulation in any essential surface, you can always isotope the surface to be normal. Other questions? All right. So now let me try to explain how this relates to the theorem. So first, let's see if we can get a little bit reduce this non-uniqueness. So if we have a normal surface, we'll define its weight to be the number of times it intersects the one skeleton. So for example, in this picture, the weight would be contributed by these points here. So I guess this picture, the weight looks like 13 or something like that. And we might as well always look at normal surfaces where we minimize this weight. So you should think of this weight as this is like combinatorial area. And in fact, normal surfaces, you can think about they're combinatorial analog of minimal surfaces. In fact, if you picked a Riemannian metric where you sort of concentrated the mass of the metric along the one skeleton, then in fact, the weight of the surface is pretty much going to be its area. And a lot of the underlying theory, which I won't get into, can be kind of motivated by this connection to minimal surfaces. But for us, it's just some notion maybe of the complexity of the surface. The smaller the weight, the better. And so let's look at what I'll call a least weight surface. So these are essential normal surfaces, which are least weight in their isotopy classes. And so now at least, while there may be multiple least weight surfaces in an isotopy class, there's only finitely many, right? Because if I bound the weight that bounds the number of times our surface can intersect the one skeleton, there are only finitely many normal surfaces with, for example, weight less than 100. So at least we kind of gone from non-unique to sort of up to finite ambiguity, which for the purposes of a talk is going to be good enough. All right, so we have these surfaces that we'd like to, the goal is we're going to count the least weight surfaces and kind of worry about the isotopy later. And so it turns out that these surfaces have a lot of structure. So, right, so I mean, like my picture here, right, the lattice points represent normal surfaces. And maybe, maybe this is an essential surface. Maybe this is a non-essential surface. Maybe this one's non-essential, right? That you ask, okay, is there any kind of structure to which points are essential or not? And in fact, in general, not really. But when we focus on the least weight ones, then a structure does emerge. So like maybe this is a least weight surface. So is this. And maybe, okay, maybe this one is here too. In this situation, it turns out that if we look at this face, right, so we have this polyhedral cone P, this green face of this, it turns out that in the situation I drew, every lattice point in this face would actually have to be a least weight surface. And maybe this is a least weight surface here too. And in that case, well, everything on this face, well, I guess it's just a ray, but everything on this face would also be a least weight surface. So there's these results of Tollefson building on work of Wortel that says that every least weight surface lies in a least weight face. And a least weight face is one where every lattice point in it is a least weight surface. So in particular, like in my picture, given that we have like a non-essential surface here, the main face of this cone, the top dimensional face, isn't going to be a least weight face. So there'll be no least weight surfaces sort of in the interior of my cone in my picture. Conversely, on the two faces I've shaded, those are faces where every surface in it is least weight. So what this is saying is that we have this polyhedral cone. Of course, this is very high dimension, right? R to the 7t. T is number of tetrahedra. Maybe T is 1,000. Okay, so it's a polyhedron in 7,000 dimensional space. It has a huge number of faces, a gigantically complicated thing. But where the lattice points that we want to count are, they're actually local. They're just in certain faces. These special, what I'll call the least weight faces. And moreover, every lattice point in one of those least weight faces is something we want to count. Okay, so isotopies between these surfaces can be understood. I'm not going to really get into that. But we've turned this problem then of counting essential surfaces into counting lattice points in certain faces of this polyhedral cone. And that is exactly where these quasi-polynomials first showed up in mathematics. So the work of Ehrhart in the 1960s showed that when you start counting lattice points in polyhedral cones like this, the result is a quasi-polynomial. Maybe the very simplest form of Ehrhart's result might be, so let's say we have a Q compact convex polyhedra in, I don't know, R to the D. Let's say the vertices are lattice points. All right, so we're just thinking like simplest example. All right, here's Q. In 2 dimensions, it's just a square with unit square on the origin like this. Then what Ehrhart shows is that if you look at, there exists a polynomial, an honest polynomial, not a quasi one, with integral coefficients, such that if we look at, if we take our polyhedron Q and sort of dilate it by a factor of S, S is going to be some integer, then the number of points, number of lattice points in this is actually equal to F of S. Right, so in the case of our square, right, if we start thinking about dilating this square by a factor of S, S is an integer. So in this case, right, F would just be S plus 1 squared. Right, S plus 1 squared would be the number of integer lattice points in this square as we make it bigger and bigger. And if your vertices are not integral but are, say, rational, then you don't get a polynomial, you get a quasi-polynomial. But this is like the kind of key idea. And so in fact, what we're doing here in our setting, like maybe we have some, here's one of our faces. And we're counting surfaces, right? This is the number of surfaces with Euler characteristic minus 2n. It turns out that the Euler characteristic function actually makes sense as a function on this cone. And so, maybe these are the correspond to genus 2 surfaces. So this is like Euler characteristic minus 2. This one's genus 3. Euler characteristic -4. And maybe this is where Euler characteristic is -6. So this turns out to be linear. And so looking at which surfaces have a particular Euler characteristic is like looking at sort of intersecting our face here with level sets of a linear function. That's very much the same thing as this. It's like, in fact, you can think about it as we're taking maybe the inverse image of -1, so that's like something like this, and we're dilating this thing out to get where the Euler characteristic is -2, where it's -4, where it's -6. And so in fact, the question we have actually turns into this setting of Ehrhart. And so therefore, the count is a quasi-polynomial. No questions? I mean, the big picture is just that if we want to count surfaces, we really only have to count these normal surfaces. And the normal surfaces, they correspond to lattice points in some polyhedral cone, and there's machinery that exists to do this kind of count. And I mean, really, I mean, I've kind of hidden this whole issue of isotopies, which is the source of all which is really kind of annoying. And to do that, I mean, you can't actually, because of the way it works out, you can't just use the work of Ehrhart. I mean, we had to use some much more recent theorems in this genre in order to prove the theorem. But I think this is kind of the overall picture. Okay, so let me just try to put this in a little context. So, you know, we have now this, for each three-manifold, atoroidal three-manifold, we have these counts and they form a quasi-polynomial. And we can ask, okay, what is that? What is, for example, the degree of that quasi-polynomial? What does it mean? And well, we are able to characterize that. So there's another perspective on this, which if you're familiar with sort of surfaces and thinking about measured laminations on surfaces, you might be familiar with, and otherwise this is just a side you can ignore. You can think about essential surfaces as being lattice points in some space of measured laminations, analogous to the space of measured laminations on a surface. In the three-manifold setting, I mean, for surfaces, the space of measured laminations is just R to the 6G minus 6. It's well understood what it looks like. For three manifolds, it's not necessarily even a manifold. It's some kind of piecewise linear stratified space. Anyway, it's not so important except to say that it has a dimension. If we're thinking about counting lattice points in this piecewise linear space, it turns out then what's going on is that the degree of our polynomial is the dimension, well, dimension -1 of this topological object associated. So that's like sort of the meaning, at least, of the degree comes from measured laminations. Another thing I want to say is that the fact that this is growing polynomially has to do with the fact that we are talking about, this was a count of embedded surfaces. If instead we allowed ourselves to look at immersed essential surfaces, just a map of a surface into our three manifold, which is injective on fundamental group, then in fact there would be many, many more. So Kahn and Markovic proved that if we have a closed hyperbolic three manifold, and the kind we've been talking about, atoroidal manifolds, then the number of immersed essential surfaces of genus G grows like G to the 2G. So I mean, it always grows independent of the manifold, it grows super exponentially. Whereas the embedded ones, the ones we've been counting, grow polynomial. Other questions?
So yeah, so is it easy to see why this should grow with genus, like number of higher genus surfaces, why it should be higher? Like,
in which setting? In the setting of our theorem or the setting of Kahn-Markovic?
Yeah, I mean, yeah, in Khan Markovich said.
Oh, well, so I mean, what's a good? I mean, I think, well, I mean, you know, the I mean, I don't think this is really very informative, but you know, as your surface gets bigger and bigger genus, I mean, you can think of it as therefore being bigger and bigger area, right? In fact, the area, you know, if we think about this like a minimal representative or something, its area is going to be more or less proportional to genus. So, you know, as the thing gets bigger and bigger, I mean, you could think of, you know, these surfaces they construct are sort of, they're almost geodesic, they're almost flat. But at each stage, you sort of get to bend them a little. And of course, the more area you have, the more choices, more places you get to bend them slightly. So maybe the more of them you're going to get.
Okay.
Right. I mean, it's like you should think of in particular, like on a surface, you should think about this as saying, well, how many geodesics are there of lengths? So instead of, you know, because genus translates to area, the analogous question on a surface would be like looking at how many curves are there, how many essential loops are there on a surface of length less than L. And of course, that's going to grow exponentially in L.
Yes, yes.
Yeah, so you think about that analogy.
Oh, thanks.
Yeah, welcome. Other questions? Okay, so you know, the fact that this you know, turns into looking at lattice points and so on, gives it a combinatorial flavor, and that's where these algorithms came from that I hinted at earlier. We're able to do a bunch of examples. I mean, let's just, I don't know, here's some pictures. Here's the Conway knot we had before, right? So we have, you know, this polyhedral cone, and then there's parts of it that give us our least weight surfaces, these least weight faces. And so, okay, what's a cone? So we could kind of take a cross section of that cone to get a convex polytope. For the Conway knot that we started off with, this is sort of a cross section of the relevant cone. The color of the vertices corresponds to whether they're genus 0, corresponds to sort of genus 0 surfaces or genus 2 surfaces. Sorry, genus 2 or 3. And then this is the final sort of generating function promised by the theorem. Here's another example. Anyway, well, maybe just say that, you know, you can do computations. So let me then to end with some open questions. What about the question I started with, right? So, you know, we're talking about counting surfaces by genus, and I said I don't know what kind of pattern these things. You can just ignore this. What kind of pattern these numbers have? I switched to counting surfaces that might be disconnected, and then there was this structure, this very rigid quasi-polynomial structure. So that's sort of what we understand. We could go ahead and ask, well, what about just counting the connected ones? You know, just as a computational question, that's a question about deciding which of our lattice points that we're counting correspond to connected surfaces. And so, you know, for any given surface, this is not hard. It's made up of triangles and quadrilaterals. You could just glue everything up, see how many components you have. So that allows us to do computations, but it doesn't allow us to see what the pattern should be. And so maybe I should say that, you know, even for the case of dimension down, for looking at curves on surfaces, this is actually a very subtle question that was studied by Mirzakhani. So in particular, what she was looking at was embedded curves on surfaces, or more generally multi-curves, so they're allowed to have more components, just like we did here. And it's well known that if you're on a genus G surface, the number of multi-curves of length at most L grows like L to the 6G minus 6. But then you can ask, well, what about, say, just the connected surfaces, or sorry, just the connected curves, or what about the curves that divide your surface into two pieces of this genus and that genus? And what she showed was that, in fact, those also sort of have well-defined probabilities and counts that uses sort of techniques that we don't have access to in 3 dimensions. This sort of anyway. So this is a hard question, is what I'm saying, even in the case of surfaces, curves on surfaces. And so far we only have there's only 2 results really about these counts. And of course, there are many manifolds for which all the counts are simply 0. And like, for example, the exterior of a 2-bridge knot, right? That example of Hatcher and Thurston from the very first slide. So there are those, of course, in that case, we do know them all. They're just 0. So my student Sharon Lee gave the first example where it's been proved what these counts are for all G where the counts aren't just 0. So in particular, what she showed is for this particular knot, some 13 crossing knot, there are 2 surfaces of genus 2. And then for genus G, bigger than 2, the number of surfaces is exactly the Euler phi function of G minus 1. So it's the number of numbers that are number of divisors of G minus 1. And my other student, Brandon Basillo, he showed the same thing for Montesino's knots with 4 rational tangles. So this is an infinite class of knots. For example, this would include things like 4-strand pretzel knots. So if we take four boxes like this, and maybe I don't know, we put some numbers in here like this. So this means we take, say, 2 things here and 3 things here, and so on. It turns out that for this, the number of closed essential surfaces is given by this formula, times a factor of 4, but essentially by the same formula. So for these, so at least for these families of examples, we do actually understand the pattern. And it has something to do with some elementary number theory, related to whether certain numbers are co-prime to others. And this sort of pattern is something that, so we've seen basically 88 distinct sequences of these numbers over the examples we computed, which was tens of thousands of examples. There are surely infinitely many, but these are like the ones that show up in kind of these small examples. And for 54 of them, we conjecture that we have a conjectured answer for what the pattern is. This was the very simplest one that we found, simplest pattern. But the other 34, we continue to have no idea what the structure of these counts are. But okay, so if we don't know what the pattern is, well, we could at least ask what are the asymptotics of these counts. And as you see from this kind of example, it's actually, it's going to be something that kind of oscillates around depending on the divisibility of G or G minus 1. So it makes sense to smooth the sequence. So let me define AM bar of G just to be the sum of AM of K for K less than G. Okay, so that then turns the Euler phi function to something reasonable like G or something. So then we can ask, what are the asymptotics of these sequences? And well, here the best I can do is a conjecture. So we conjecture that either these counts are all 0, for large G, or there is a natural number S, so that if you look at the asymptotics of these counts, then they're asymptotic to some multiple of G to the S. And this plot here is some data that we accumulated in our paper in favor of this. So each line here corresponds to one manifold. On this axis is the genus. So we're going from genus 0 out to genus about 200. So these are log scales on both sides. So this is the number of surfaces of genus at most G. So it's a log-log plot. So something like, n to the S will appear, or sorry, G to the S will appear as a straight line. So these dotted lines, these are just sample lines of slope 2, 3, and 4. And then you see that the observed data, kind of comes in these families. There's a family where the slope is 2, a family where the slope is 3, the slope is 4, slope is 5. So they do seem to grow, not just like G to some power, but G to some integral power, independent of whether they're sort of this kind we have a conjecture for the pattern or the kind we don't. So there's a lot of data behind this, and of course, so that's the conjecture. And maybe I should end by saying, so main theorem was that these counts have a structure, and like most talks, I told this story all backwards, right? So we started by being interested in these counts, and we were first interested in genus 2 for whatever reason. So we started writing programs to try to compute these numbers, and then we thought, well, we should. What happens in genus 3 or 4? Well, it wasn't so hard to modify the program. So then we started to have some data, and then started looking at this. Well, should there be a pattern? Eventually we figured out there was a pattern, and we figured out why, and so on. So this was really all motivated. The main result was really motivated by experiment. And so here's some more experiment, which I hope will motivate further results. So that's all I wanted to say. Thank you for your attention. Let me stop here. Are there questions?
Oh, any question? Yeah. Please ask. Okay. I think there is no question. So thank you, Professor Nathan Dunfield. I will again very thankful to you for accepting our invitation.
My pleasure.
Yeah. Thank you, all of you.